Okay, I'm going to be presenting my recently published paper in PLOS ONE. It's titled Interpretable Machine Learning, and sometimes people call this Explainable AI, with tree-based Shapley additive explanations, application to metabolomics datasets for binary classification. And this work is just going to be a pretty short video abstract, just going through some of the main points that are presented in the paper. Okay, so let's get started. So machine learning models are used in clinical metabolomic studies, most notably for biomarker discoveries. And you identify metabolites and you want to discriminate between a case and a control group. And in this domain, modern interpretability is quite very important. So in the domain of biology, in the domain of biomedicine, you really want to understand what's going on and why your model is really predicting that output in quite a lot of the cases. In metabolomics, which is in the context in which this study is taking place, partial list discriminant analysis called PLSDA is widely used. It's a widely used machine learning tool, and its model interpretability method is something called a variable influence on projection, called VIP scores. So you hear me say that a few times in this talk. But in this work, what I did was then to use tree-based Shapley additive explanation. That's called SHAP, TreeSHAP, if you will. It's an interpretable machine learning method that allows you to explain both local and global interpretations. More of that in a minute. And I did some machine learning experiments and of course showed that this TreeSHAP method is actually quite a powerful method for really interpreting machine learning models for metabolomic studies. So let's get it started with some background. Let's start with metabolomics. When you're talking about metabolomics, of course, you have to talk about metabolism. And a very good analogy that I found quite useful is to think of metabolism in the context of as analogous to a railway system. So in a railway system, you have major pathways. So your major pathways would be railway lines. You have key metabolites. So key metabolites would be a railway station. And between the railway station, what's happening there is biochemical reactions are actually taking place. And in metabolomics, what you want to do is you want to measure these metabolites, the small molecules. And the way you do that is you use analytical chemistry techniques such as NMR, nuclear magnetic resonance, use mass spec, and in short, you kind of like summarize. You could then think of metabolomics then as a study of the small molecules, which are called metabolites. They are produced by living organisms and they are reflecting biochemical processes and overall health. So just imagine that in a particular railway system, you had chaos, you had an accident, or you had an attack, and that's really going to affect when people are able to get to their appointments, because suddenly now you have people not able to board their train. And that's really going to affect, if that happens well enough, it's going to affect economic activity in that society. And that's the same analogy that works with metabolomics, right? Or with metabolism, rather. You take measurement of these metabolites and it tells you exactly what's going on, whether it's tending towards disease states or just to tell you about the overall health in general. So now let's talk about interpretability. So machine learning model, a very simple example would be you have a model, you have a sample, and you want to make a certain prediction, right? And after you've made that classification or prediction, you're asking, why was that prediction made? There are different ways to really think about the techniques out there. So the XAI is called the Explainable AI, IML is called Interpretable Machine Learning Methods, and the different ways to really think about how you classify them. You can classify them in the context of intrinsic methods. So these are machine learning methods that are intrinsically interpretable, or post-hoc methods. So these are methods that are interpretable methods are applied after you have actually built your machine learning models. It could be local or global interpretations. Local simply means you explain individual predictions. Global means you explain the entire behavior. And you can also think of it in the context of the results of interpretation. So if you have a feature summary statistics, that will be an example of a PLSD AVIP score. It could be a visualization method such as the partial dependence plots called the PDP. And also in context of model internals. If it's model internals, then we're talking about the weights in linear models or the learned tree structures that you have in decision trees. And the interpretable models versus the model agnostic models. And this is quite some overlap with these first classification, but not quite perfect overlap. But if you think about interpretable models, you're talking about linear regression, decision tree, PLSDA, and if you're talking about model agnostic methods, these are methods that you can apply to any machine learning models irrespective of what models they have. You can have the partial dependence plots, you can have highs, you can have line, and you can have Shapley additive explanations, which is called SHAP, and that's going to be what I'll be talking about in this short video. Okay, so when we talk about SHAP, Shapley additive explanations, it's an adaptation of the idea of Shapley values, which is was first presented by Lord Sharp in game theory. So it's a concept that actually comes directly from game theory. So Shapley values essentially just tells us or gives us an axiomatic solution to really fairly distribute payouts to players in the game. So if you bring that idea and bring it into the context of machine learning, then we are really thinking of features in your X matrix as players, and then you're thinking about the prediction that are made in the context of the payout. And the question is, how do we attribute fairly the importance of the contributions of each of these players to the eventual payouts, if you will? And you do that using Shapley values. And the way you compute it is that you can compute marginal contributions. So you compute marginal contributions, and you assign weights to those marginal contributions. You of course sum that up. You take your average, and then you get your Shapley values. Shapley values are, again, I said previously, it's a way that actually fairly distribute payouts, and that's because it really guarantees some pretty important concepts. And then the first concept is the idea of symmetry or consistency, and that simply means that if you have two players in the game, or let's say two features, if they have the same contributions to the model output, so the same marginal contributions, of course, for all combinations of the subsets, then the Shapley values, their importance will be the same. It guarantees that. It guarantees that if the features have, if the marginal contribution of a certain feature is 0, that in fact the Shapley value will be 0. And quite importantly, if we take individual Shapley values, we can add these together, and that can actually explain the entire model. And this is the case of what we call the additivity or the local accuracy rule. So all of this actually makes SHAP very attractive. Now let's not talk about TreeSHAP now specifically, because we are using a particular kind of SHAP called a TreeSHAP. If you want to compute naive Shapley values, how do you handle missing features? Okay, because that's what's going to be happening when you're computing marginal contributions, and of course computing that will actually involve exponential computational time. TreeSHAP actually helps you do that quite efficiently, because you can calculate exact Shapley values by ignoring decision paths of the missing features in the tree, and also it actually helps to reduce the complexity of the algorithm. And this is essentially because we can leverage on the framework of the tree and efficiently transverse these three paths, these decision paths, if you will, as we are actually computing the Shapley values. So the TreeSHAP is quite superior in that sense. So now let's go back to my work and then look at just kind of like metabolomics workflow. Very briefly, you would have biofluids from, this would be a sample, it could be urine, it could be serum sample, you do your metabolite measurements, you do your pre-processing, you process your data sets, and if you want to make certain kinds of classification, if you want to make regression, you train your model, and then the model can then be explained with SHAP, just like I've been talking about. So for this work, I actually looked at 3 data sets to do the initial machine learning. A data set that is actually used in this case for sex classification, and these are adults, human adults, male and female urine samples. Another data set that looks at the impact of high-fat diets in the cecum of mice, and then another data set that's looking at an adenocarcinoma lung cancer using serum samples. Okay, so for my machine learning pipeline, I used I actually did a comparison between PLSDA, which is the method that I talked about to be quite predominant in the field of metabolomics. And then what you're looking at here, and this figure is present in a supplemental figure, I believe, is the keyword occurrences per year. I plotted that out of keywords reflecting PLSDA, random forest, and gradient boosting in PubMed. I think this is up to the end of 2022. Then you can see that PLSDA is actually quite used a lot in metabolomics. So what is my pipeline? So my pipeline, essentially, you have your data sets like I've described previously. I do feature selection. I transform my features appropriately, and then I do machine learning to compare these 4 different kinds of machine learning methods. The PLSDA methods was actually explained using the variable importance and projection, and a tree-based method was actually explained using SHAP, using the TreeSHAP. And of course, I did hyperparameter tunings as expected, and so on and so forth. Okay, so what does the result look like? So this is the result, and these are the models I used. For each of the 4 models I used, I have the baseline, and I also have this tuned, the hyperparameter tuned version. And this is the biological sex classification problem. This is a high fat diet classification problem, and this is the adenocarcinoma lung cancer classification problem. Okay, so what do we have here? So what we have here is, and you can check details of this in my paper. So we have a training data sets, results. This is the raw KUC values for 10-fold cross-validations, while below you have your test scores. For the sake of this talk, and largely in my paper, I really focused on this random forest model for this biological sex classification explanation. And why did I choose that? Well, first, because it has a high predictive score. So the AUC value is 0.83. It's not the highest, but it has a diversity of errors, which actually allowed me to do some explainable, to show the utility of how you use explainable here. And then also because it's kind of like straightforward, the simplicity of some of the results that I am going to show. Okay, so first you have your global feature importance. Again, this is when you explain the entire model. And in panel A, what you're seeing is the explanation for the PLSDA model. Okay, so they use the PLSDA model. And again, this is the VIP scores ranked in descending order of importance. In B, this is for the SHAP value, again ranked in descending order of importance. In C, this is a scatter plot that's plotting the VIP scores against the SHAP values. And you can see a slight positive correlation there, showing that there is some kind of similarities in the way these 2 models actually explained their predictions, if you will. And you can think of this graph as a control, whereby you're plotting the Gini importance scores against the SHAP values. And then what you have here is basically the fact that SHAP is explaining it with quite high amount of fidelity, at least with respect to the gain importance score generated by random forest. Next, summary plots. And in the summary plots, this gives us a much granular detail. So on the x-axis, you're seeing the metabolites. Again, these metabolites are arranged in order of descending importance. Okay, so the most important is at the top, the least is at the bottom. Again, the details are actually shown in here. And each dots that you have here, represent a sample. Right? It represents, in this case, a urine sample. And then you can see that each of that dots is actually color-coded by the relative abundance of the metabolites, right? And the plots on the x-axis is essentially the SHAP values, which describes the impacts of what we're explaining on the model outputs. So I'm just going to go into the most important model to explain in a little bit more detail what's going on. So the most important metabolite here, in this case, happen to be a metabolite of testosterone that is actually found in the urine samples. And again, the original data sets that was used for this is actually aimed to look at how quite a lot of potential co-founders in metabolomic studies affects metabolomic studies in general. So the original paper look at things like age, BMI, and I think sex. So in this case, I'm just using it for the male and female discrimination. So again, looking at the testosterone glucuronide, in summary, high amount of these metabolites of testosterone is associated with male prediction, while low amount of these testosterone, that's low amounts, that's the low relative abundance of it, is associated with female, or like the female predictions. So that's how you just go through the summary plots. Another avenue for explanation is the local explanations, and this is what methods like the PLSDA won't give you. They can't explain single instance. So in this case is a true positive sample. So this is a male, classified as male by the machine learning model. And this at the top, you're seeing the force plot. So the force plot is showing us exactly what metabolites are driving our prediction to 0.8. So this is the probability of the output. So 0.8, if it's higher than 0.5, is male. If it's lower than 0.5, is female. And this can also be described in the waterfall plots. And the waterfall plot, you're seeing the metabolites, you're seeing the probability outputs, you're seeing the impact of each of those metabolites on the output. And again, quite obvious here is the metabolite of testosterone driving the prediction towards male. And this is how you essentially try to understand the local explanations. So going much deeper into these, when you have a tool like this, you can do things like error analysis. So what's really going on? What can I check? This is no longer a black box. So what's really going on with my predictions? So these are confusion metrics that's breaking down the categories of all predictions. Let's look very quickly at the true positive prediction. And the true positive would be male samples that are correctly classified as male samples. And quite off the top, you see that the testosterone, the testosterone metabolites is actually high in these samples. And of course, it's the primary driver, or it's one of the most important driver of the prediction towards a sample being classified as male. And in a female, in a false negative sample, that would be a male that is, by this machine learning model, wrongly classified as female, is actually quite missing the metabolite of the testosterone. So that could be a probable reason why this wrong classification is made. Going forward, let's look at true negative samples. You have a female correctly classified as female, okay? And again, these are largely driven by very low levels of that metabolite of testosterone. You can see that here, and you can see the probability output of the machine learning model. And false positive, the first positive are the female sample that the machine learning model wrongly classified as male. And in one of that, you have a fairly high abundance of that metabolite of testosterone, that's the testosterone glucuronide. And the other samples, you actually have a low levels of the metabolite of testosterone. However, it's just right at the edge of being predicted as female. Okay, so it's pretty much close. So in essence, this is what having access to methods like TreeSHAP actually affords you to actually potentially even debug your model, if you will. So in the paper, I also presented result on the impact of a high-fat diet on bile acid in the cecum of mice. And basically, the original study was to study how dietary facts induce bile acid changes in the gut microbiome in mice. But I presented the results in my paper, but I am going to just go straight to the conclusion at this point. This is meant to be just a very short video abstract. TreeSHAP is desirable as a post hoc interpretable method because it actually enhances the interpretations of the metabolomics data sets. As you can see, it affords us to see local, global interpretations. You have high expressive power, it has high fidelity. And then you can just take a look at my paper. It's just published in PLOS ONE. And thank you for listening.